All right, gang, Math 6500. This video follows up on identifying influential cases, and the timing of this is at least if you're getting close to your master's thesis, where you're going to be, dealing with real data and real problems and things like that. So identifying influential cases are extremely important once we get to that stage. So the timing of this has actually been really, really good for those of you at that stage. So guys, after finding Y outliers and or X outliers, we kind of switch our focus here, and we want to focus more on whether these cases are influential. So that's going to be an important term here, okay? Are the cases influential? Do they influence our model? And guys, at the end of the day, influential just means that excluding the case under investigation affects the fitted regression function to a substantial extent. So, so again, influential, what does it mean? Removing the ith case. I don't know how I want to say this. Let's just say affects the fitted regression function, regression model. So again, any case that has a kind of a drastic impact on the fitted regression model, we call that an influential case. All right, now what we've seen so far, and this is going to come to play a role in this video, is let's say that we have a situation where we have, all sorts of, just really cool linear relationship between some data. And but between x and y, for example, and let's look at some outliers. For example, this would typically be considered an outlier. Now, would it be problematic? Whoa, I have no idea what happened to my deal. It probably wouldn't be problematic, because if I examine this level right here, and let's just call that x level 1 or whatever it may be, there's enough other points at that level that's kind of going to soften the blow of point number 1. So at point number 1, I would say not problematic. Let's take another look at, say, a point number 2. That would probably be considered an X outlier and a Y outlier, considering the variation in our X and our Y. But in terms of changing the estimated regression function, you can see that the point number 2 would lie very close to it. I would say this is probably not problematic or influential either. Now, guys, get into a case like this, case number 3, or forbid case number 4. Guys, these could be problematic. Case number 3, when I look at the variation on Y and I look at the variation on X, case number 3 could be considered an outlier to both X and Y. Case number 4 would not be an outlier with Y clearly, because it fits kind of in the central focus of our Y, the variation around the mean on Y. However, it clearly would be an outlier for x. So guys, points 3 and 4, potentially influential. Let's see, I can spell, I just can't see, guys. There we go. So these could be potentially influential. Now, guys, I just like this stuff. I just remember when I did my very first research, and I think I've mentioned this before. Let me get my computer set up here where I've kind of got it in the way. All right, sorry about that. I don't want you to go blind on me. And again, I learned firsthand after I collected some data how cases can be influential. So guys, we're going to examine 3 measurements of influence. The first one we're going to look at is called Dffits. What Dffits does is it looks at the difference in the predicted value for a particular case when it's included in the model and the predicted value for that case when it's not included in creating the model. I had to review more about Dffits because I wasn't as familiar with Dffits as I am the other two. Guys, Cook's distance is a similar measure in that it examines the fitted value for a particular case, but instead of comparing it to the predicted value when the case is deleted, it looks at it over all of the n-observations. So we'll see that play out in this video. And the one that I'm most familiar with, and the one I think that of the 3 is the one that tells us the most, is called DF betas, and this is going to be in the next video. So guys, in this video right here, I'm going to try to give you a brief introduction to Dffits and Cook's distances. Now, you're going to see a lot of similar stuff play out here in terms of using standardized regression. Guys, I tell you what, I'm just not happy with the way that things are working here. Let me get things going a little bit better. All right, still not happy with that, but that'll just have to work. All right, guys, let's go ahead and get into these Dffits. And Dffits, and the reason I put this in I, is they measure the influence the case I has on the fitted values. So let's put that measures the influence that case I has on the fitted values. And it turns out that Dffits are really easy to create. Take a little bit of work, but you know. So you know, most things that are worthwhile do take a little bit of work, right? So Dffits for the ith case is to take the predicted value of the ith case minus the predicted value of the ith case when the ith case is deleted in creating the regression function over the square root of the mean square error with the ith case deleted times the value on the diagonal for creating the HAD matrix. Now, at the end of the day, guys, DF stands for difference. So what you can think of is this is just a difference in the fits. This y hat sub I, as you should know now, is the fitted value for the ith case when all n cases are used in creating the regression function. So the fitted value for the ith case when all cases are used to create the regression model. Now contrast that with this notation, which is y sub I sub I. Well, not really y sub I, but y sub I, and then well, you see what it is. Okay, I don't want you to think it's y sub I and then sub I down here, but so anyway, you see what it is. It's the fitted value for the ith case when, well, let's put it this way, using the regression model that was created with the ith case deleted. So let's just say that we've got a sample size of 50. Well, this one up here is going to give you a predicted value using all the cases. But we've got one particular case that we want to examine how influential it is in our model. So down here, we're going to create a model using 49 cases, the ith case deleted, and make things happen from there. Now, guys, our denominator, let's just focus on this right here. What happens there? Think of it as like an estimated standard deviation of our y hat sub i's, but it's comprised of the mean square error when the ith case is actually deleted. So, guys, our denominator is in standard deviation, so it produces for us a standard measurement, if you will. So it gives us the number of estimated standard deviations that our predicted value increases or decreases with the deletion of the case that's under investigation. Now you can repeat, I'll be glad to repeat it again, our denominator, if I can. Our denominator is in estimated standard deviations. Notice we have the mean square error, so we've taken the standard deviation of it. I'm sorry, we've taken the square root, which converts it to kind of a standard deviation measure. So it's the estimated standard deviation of the fitted values for y sub I, but it's, from this notation right here, it's the mean square error when the ith case is actually deleted. And I'm going to demonstrate this stuff to you in just a second. And again, keep in mind the denominator is in standard units, standard deviations. So it gives us a standard measurement for comparing the fitted value when the ith case is in the model and when it's not in the model. Okay, so hopefully that all comes together via an example. Now, let's just look at an example, and I'm going to go back to an old friend, body fat example. Let me get this down here where you guys can see it. So we're going to use the body fat data set. And if I remember correctly, the I equal 3 case was causing issues as a potential X outlier. I hope I'm right on that. It's been a couple of days since I put that other video up, but I think that's what we found. So guys, what I'd like to calculate, so I want to show the calculations for D sub 3. I'm sorry, DF fit. Actually, it's DF, Doug. DF fits for the third case. So guys, here's what we're going to need. We're going to need DF fits for the third case, for the predicted value for the third case, minus the predicted value for the third case when the third case is deleted, over the square root of the mean square error when the third case is deleted, times the H sub 3 from our hat matrix. So guys, I'm going to keep this organized here. So first thing I need to do is calculate this value. Next thing I need to do is calculate this value. I also need H33, that's going to be the easy one. And then I need the mean square error when the third case is actually deleted. Okay? All right, gangs, everybody on board here? Hopefully you are. If not, you need to get on board. So I've already got body fat. Uh-oh. I'll take that back. I don't have body fat open. I had it open. It doesn't matter. Well, it doesn't take long. All right, guys, there we go. We've got attached data, we got the names, we've got our variables, and we should be super familiar with this data set. Okay? Now, guys, I'm going to go ahead and create my X, my design matrix, because I'm going to need that to calculate my H sub 3, okay? So I'm just going to go ahead and get that out of the way. So, you know, I just do it this way. I know some of you don't, and that is perfectly fine. Guys, I got to admit, I don't remember whether the sample size is 20 or I'm pretty sure it's 20, so it'll just give me the length of triceps. That'll do it. Okay, so sample size 20. So, I need my ones, which is a repeat integer situation, 20 of them. And I want my design matrix, as we've done many times before. So I'm going to do two predictors here. So I'm going to do my ones, and then I want triceps and thigh. Yeah, let's go with that. So in rows are going to be 20, and columns are clearly going to be 3, and by row is equal to false. So guys, just take a look at that, make sure it's what we need, and it is. So guys, the hat matrix is going to be really easy. So remember, we have X times the inverse of the transpose of X times X times the transpose of X. All right. Now I don't need to see all that. If that kind of stuff turns you on, then hit, type H, and you'll see a bunch of stuff. You'll see a 20 by 20 matrix. But really, all I care about is the diagonal on H. So I want the third one. So guys, I can come to the third entry. So point .3719 is the value for H33. Because I'm over here, hopefully, as you, writing .3719 for H33. Now, gang, the next thing I need to do is I need to make get my predicted values. And remember, you can get your predicted values a couple of different ways. You know, we could just straightforward run a model if we like this, and do body fat, you know, tilde, so on and so forth. But I want to show here, I want to use matrices to do this. So if I can create, well, what in the world? Create the Y matrix using body fat. All right, so I don't need to see that. Okay, now remember, guys, my my fitted values can be found by taking H times Y. So what I need here is I need the fitted value for the third entry. So that's 21.876, okay? So that's my value for Y hat sub 3. So that's 21.876. Now, gang, my focus changes. So you can see where I wrote this down. Guys, my focus now changes to these two calculations. And these two calculations are a little tougher because we need to delete a case and kind of rerun stuff. All right, so I'm going to show you what I think is a pretty easy way to do that. And I'm going to create some new data. And what I want to do with the new data is let's see. Okay, let's see. I want to, shoot, I didn't write this down. I want to take my data set that I have, and I call it data from the get-go. And I want to subtract the third case. And then I've got to leave a space right here. Notice I left a space because when I have data bracket, the default for this, or the form that it's looking for is, first of all, it wants to examine the cases that you want to do something with, and then it wants to look at the variables that you want to do something with. Well, I want to include all the variables, so that's why I'm leaving this part blank, but I want to subtract out case number 3. So I want to, back in my initial data set, well, I didn't have it, but right here, I want to delete the 30.7 and 51.9, okay? Now, I usually don't do this, but I want to make a point. If I type my new data, notice that what it's done is it's deleted subject number 3. Now, I still have to ensure that R isn't going to make my calculations based on the data set that includes 20 observations. So what I've got to do is I've got to attach new data, and when I do that, it is going to use the last data set that I attached in the calculations. So, for example, I have triceps right here under two headings, my data set named data and my data set named new data. However, because I attached new data last, when I do length, of, for example, triceps, it's going to give me 19 because it is focusing on the data set that was attached last. Now, this works really, really well for new calculations. So I'm going to go all the way back up here, and I'm going to create my X matrix. But guys can't do that, can I? I forget I did that. What I've got to do now is I've got to create some ones, and I'm going to call this new, and repeat integer. And I need ones, but I need 19 of those. All right, now I can hit my up arrow, and I can go all the way back up to what I need, for example, to get my X. But guys, I need to make some changes. I need my ones new. And I need in row to be 19 and not 20, but everything else is going to work. Now, gang, when I get X now, again, I typically don't do that, but I want to show you that it's deleted the third case. Okay? Now what I want to do is I want to go back up and get the form for my hat matrix. And now how do I need to change that? Well, I don't need to change it at all. And notice I have a 19 by 19. Now guys, I want what do I need? I want y hat 3, 3. Okay. So now what I need to do is I need to get my fitted, well actually I need to create my coefficients. Because since I don't have the third case in my model, the model that I create from this information, I'm going to have to kind of plug and chug here. So I'm going to create my betas, and that's going to be really easy to do. Well, guys, it's not going to be easy to do. I got to go back and get my y's. All right, so okay, now I want to create my beta matrix. So guys, remember we have solve transpose x times x times transpose x times y. So the coefficients for my model are this. Now, guys, I got a little bit of work to do. I have to go back up to my original data set, and I have to pull out the case that I deleted. Now, you got to be really careful because the third case down here is actually the fourth case from the initial data set. Notice it's been deleted. So I got to go back up here and make sure that I'm pulling from the right data set. So the observation that I need to predict using the new model is 30.7 and 51.9. So I need to create my new, so negative 12.428. Plus, nah, shoot, guys, I forgot, 30.7 times 0.564 plus 0.364 times 50.7, right? No, 51.9. So my predicted value here, with the third case deleted, but predicting the third case, is 23.778. So let's just do 23.7. 78. Okay. Now, the next thing I need to do is I need to get my mean square error, and I'm going to let you guys cheat a little bit on this one because I don't want this video to go too long. I'm going to create a model from body fat over triceps plus thigh. And I want my ANOVA, my model, so I can easily get my mean square error, which is 5.87. Now guys, I'm doing this to save time. You need to be able to do the calculate the mean square error using using matrices. But for the terms of this calculation, to save time, I'm going to bypass that and take the easy way out. All right, guys. Let's see where we are here. So it looks like Dffits for case 3 is going to be 21.88. Minus 23.78 over the square root of the mean square error with the third case deleted times 0.3719. And when I put that in my calculator, let's see. I get negative 1.29. All right. Now, that's kind of a cumbersome way to do your calculations. You have to kind of admit, you know, creating two models, one with the ith case in it, in this case I equal 3, and another with the ith case out of it. But it turns out there is another way. There's a way that we can use standardized residuals and just create one model. So just file this under how to calculate Dffits using the full model. And when I say the full model, what I mean is it includes the ith case. Now guys, this is going to require us to revisit an old friend called the standardized residual. And I'm going to need a whole lot of space here, so let's get over. So Dffits is about taking the error for the ith term. You know, just so I don't forget this is all to the square root. So I screwed up and didn't put the square root, so we'll just put to the 1/2 power. The denominator is the messiest. It requires the sum of squares error for the full model times 1 minus HII minus the residual for that term squared. And on the top, in the numerator, we have n minus k minus 2. There's an extra term, what I call the I guess the leverage term. Which is also, we take the square root of it. Now, guys, I'm going to leave this for an exercise for you guys to create this, but I'm going to tell you what I got. I got my error for the third term. So if we were calculating Dffits, again for the third term, I get my error for that term is negative 3.176. I have a sample size of 20, minus 2 predictors, minus 2 degrees of freedom because we have one less case, one case eliminated, and we have our intercept that we have to be concerned with. I got 109.95 as the sum squares error for the full model. 1 minus 0.3719. And then I get minus, minus 3.176 squared is the error squared. This part turns out to be easy. Raised to the 1/2 power. Now, just to make sure we're on board here, I end up getting negative 3.176. For this part, I got 0.5209. And for this part, I got 0.7695. So that's, I haven't taken the square root. And we get a little bit of rounding error here. I think in the previous video I actually got, or not the previous video, but the previous calculation seemed like I got negative 1.29. I'm sure that has just to do with rounding. So guys, check these calculations. I'm pretty sure they're correct. You know, we end up getting the same final answer, which is a pretty good indication that that all is in the good, let me get this straight here, all is good in the world of calculations. Well, let me let my dog in. My dog's going absolutely insane on me. All right, see why my dog's going insane. It's actually raining. All right, guys. Finally, what I guess at the end of the day, is what is a Dffits value that creates concerns? Well, guys, I tell you, I'm from the old school, and not many people agree with me on this. But I'm from the old school that says if the absolute value of the Dffits is well, I just had a pop-up on my screen, is greater than 2, then we have reason for concern. We could consider that ith case to be influential. And if we're reporting our results, I think you should report the results with that value, and you should report the results without that value. But people who know far more than me don't agree with me, So maybe I should agree with them. I don't know. What most people believe, and guys, really what I'm just kind of going with here is 1.96. Although this isn't an inference procedure, that's kind of the way I think about it because we've standardized things. But, you know, people don't agree with me, and they've done a lot of research. So we should believe them and not me. So let's put, just in case, focus on this. Ignore me, okay? I'm old school. Research kind of shows that if we have a smaller data set, so let's say small to kind of moderate in, that if the Dffits is greater than 1, then we have reason to be concerned. If we have a larger data set, then the research says that at least the experts in the field say that if we have 2 times the square root of k plus 1 over n, so if our Dffits is greater than that, this is what we should examine. Now, guys, I would say n equal 20 is a kind of a moderate sample size, small to moderate sample size. Our Dffits is equal to negative 1.27, which raises concern. For the third case, sorry guys, as being influential. I wouldn't report it in this. I would, I just wouldn't. Negative 1.27 to me is close enough to 1. It raises concerns, but I don't know if it would raise enough concerns for me to run a completely new model and to report those results. All right, all sorts of distractions in this video. All right, let's go on into. You know what? I think I'm going to end this video. What we do next is Cook's distances, and we'll look at that in the next video. Okay, guys, take care.